Okay, the NPTEL course is going well and good. Okay, nice, awesome. Okay, so once again, I want to introduce myself. My name is Eshan Rao. I'm a PhD student from Indian Institute of Technology, Tirupati. So every Tuesday, I'm taking this uh, interaction session where we're going to talk a little different from whatever actually going on in the data structures and algorithm course. So I want to give a little bit different perspective through it. So during this last week we have done something of time complexity. We will revise through it. That's a part one. So in part two we'll look at actual notations which we use to analyze an algorithm. Since it's a part of algorithm, so I think we all should know how to analyze an algorithm, how to say whether it's good or not, in what comparison we should say it's good, in what comparison we say it's not so good. So all these things we are discussing. So let me share the screen. We will recap through whatever we have done last time, and then we will go towards the second part of this session. Let me share the screen. Okay, so I hope you can see the screen. Okay, so what we have done last time is, as a first step, when you want to know that what is the time complexity of an algorithm, first you should identify how you should calculate it. Okay, so we have seen one method called frequency just a minute. Yeah, frequency count method, and we have seen multiple examples for it. So just to recap, we will see an algorithm. Every statement we will have a certain kind of we'll give a 1 unit of time. So every statement will run for 1 unit of time, and then we will try to calculate how many times it will run. And we usually see in terms of function. So in this, let me change few things. Okay, so in this case we are looking at function of order of n, or as a typical function when we're deriving 2n plus 3. uh, so these are different ways we have identified where we try to analyze, given a nested function, or given a normal for loop, uh, or normal iterative loops, how it will can find. We derive it through analyzing the variables like I and j, which are quite independent of each other. That is one way we look at. And then over the period of time we also look at how the functions are incrementing or decrementing in one cases. In another cases we're looking at uh, if how the condition actually change the equation of the time complexity. That is another way of looking at it. And then we have also seen uh, the the role of a particular variable, how it is actually uh, influence the time complexity of our algorithm. Also if the if the the variable in charge is actually uh, is incrementing in the terms of multiple, like it's multiplied or divided by certain things, so how the values will change. So all these things we have looked at, and we came to a certain understanding that, let me go to, that we have a certain kind of functions, that is we call a time function, that we are usually going to see in time complexity area. So we will see order of one, that is constant function, something as logarithmic, linear functions, quadratic, cubic, exponential, like 3 is to n, 5 is to n, such that. So we usually arrive at this kind of uh, place where we'll put all the time function in a single plane to understand which is bigger, which is smaller, to what extent is bigger, to what extent is smaller, what are preferable time algorithms. For example, um, okay, so for example we will try to keep algorithms. Whenever you try to create an algorithm or you write an algorithm, new algorithm or existing algorithm, we try to put inside the polynomial time. We don't even though there are many algorithms there which are in exponential, uh, that we can discuss another time, that they will be like factorial is one of the exponential algorithm. So in such cases we try to avoid such function, but if we can't have it, we have to keep it at certain place in the time function space. So that's why we have this exponential functions. So both this time functions will give a certain idea of how are the things, what are things with this algorithm, how we can analyze them. That's a first step. So once we identify that, okay, this is the time function of a particular code snippet or particular program is like this. Next is we have to mathematically define them and first do some notation, and we have to understand which function is bigger than which function, and how we can solve them, how we can identify such functions. If we have two codes are given to us and two time functions are there, how we can identify which is bigger than which. So that is something we are going to look at in this session. So let me go to the new current session. So here again our focus will lie within this space of time function. That is one is the here the function when we are saying is this one is constant function, constant time function. Log n is a which is greater than the constant time function. Then n, that is this is a linear, so linear time function is greater than log n. So when we are saying like this, that means we are assuming that al algorithm of a time complexity of an algorithm will be within this function. We are defining like that. Okay. Now once we identify this, now come to the second part, that is the asymptotic notation. So this is something you should very careful about when you're trying to define. So when you say that my function is like this, how you should say that. If you just say n, it doesn't make sense, it will not make sense to people. So you have to define that how to present time complexity for a particular program that you're writing. So there are three different ways which we can use, that is big O, big omega and theta. So we're going to discuss these three aspects notations in this class, and we're going to solve certain things, and there are little bit confusions usually people have with respect to what is they look at this big O omega as best case time and worst case time. So they look these two functions specifically and from this lens, which is absolutely false. This is not. Big O, big omega doesn't represent big case time, worst case time for an algorithm. It doesn't. It's just a notation that we are using them. So what these notations are, how we can use it in our system, definition, we will see that. Okay. So first we'll go with the big O. So big O basically is if you have to go mathematically definition. So there's a function called fn and there's a function called gn, and we have to find the relationship between them. So so we have to define that how this function will relate, gn will be related to fn in terms of time complexity. So when we say that if there's f of n is equal to big O omega of g of n, that is g of n, we are talking about g1 of aspect in terms of big O. If there is a positive constant c and no, we will talk about it, which is so it should satisfy the condition that fn should be less than equal to c of g of n for all n greater than no. Okay, so what does it mean actually? So we have this function called fn equal to 2n plus 3. You may find it from some algorithm. Some algorithm you find this value, but usually to understanding it's not it will not give us a better understanding for that. So what they will do is we have to define them in terms of big O. So what we have to see is if there is a function called g of n which is greater or equal to this 2 of n plus 3. So I can say that 10n, suppose for example, or 15n. 15n, so if fn we have to say by g of n, so obviously 2n plus 3 will be less than equal to 10n or 15n. So this condition is valid, right? So what is here we are talking about is, so here the 10 will be considered as a c. Okay, so if we have a constant, positive constant c, from which value of n it should be value, this condition should satisfy for all n greater than equal to no. That means if n value is greater than 1, then whenever you put a value of n's here, this condition will satisfy, that is 2n plus 3 will less than equal to 10n always whenever is n value is greater than 1. So here no will be 1. Okay, so that is a brief idea. So but what it tells about, it tells about us the upper bound, it's called upper bound of a time function. Okay, so there are multiple ways to look at it, but we will go slowly towards what is upper bound of definition. So here if I say that 10n is the upper bound of 2n plus 3, it is correct. If I say n square is upper bound, because 2n plus 3 is actually less than equal to n square, which is this condition also satisfies. So we can also say that n square is also is upper bound of that. So you can just like that, n cube, 2n raised to n, all and so on, all the function which is greater than 2n plus 3 we can satisfy as saying that it's a big O of gn. So here gn can be it can be 10n, it can be 5n, it can be n square, n cube and all. So why we are usually thinking about that? We are saying this because here right now our function lies somewhere in this n side, that is here it will be 2n plus 3. So whatever bigger than this, we'll change the color possible. Okay, so I will change the color here. Okay, so whatever from 2n plus 3, whatever the functions bigger are than this, then we will call it as upper bound. Okay, that is one aspect. And when we go, whatever values are less than 2n plus 3, we will see like here, we will say it as a lower bound. Okay, so till as many aspect we can see the in terms of time complexity, we can find the upper bound of a function, and we can find the lower bound of the function. Upper bound we are looking from big O, lower bound with omega. We will discuss about omega later. So okay, so coming back to here, but if I directly say that 2n plus 3 is greater than n square, it doesn't make sense. I need a more concise value, that is a function which is more nearer to this fn. So that will give me a better practical value to understand the code or the program that we have written. So what we can do is, either you can write directly, you can manually find the value like 2n plus 3. So if you put value n equal to 1, so these value become 5. So whatever values will be you want to have here, 2n plus 3, it should be greater than value than 5, equal to 5. If I put n equal to 1, that is one way of looking at it. So you substitute some value and find the minimum nearest value. That is one way. Another way that you can look at it is, you just, is 2n plus 3 is there, right? You just have this 2n plus 3n, you just add another n here, and then you can say 5n. Okay, that is one way. Or you can say that 2n plus 3 into, and then you can add some constant here. If you have this constant, will tell you that okay, because here you're multiplying, or 2n plus 3 is only 1, but if you add some constant multiplying with that, obviously that will be 10x more than that. So that's another way. So for this f of n, nearest one we can say for now 5n, and that is quite okay. But same sorry, g of n will be 5n. Similarly, g of n, if you put it n square also, this is okay, totally fine. But since we need nearest value to fn as a upper bound from where it can start, then phi n would be a better answer. So that is the upper bound. The more we solve the problem, the more we will understand, we will get to know about this big O definition as well. Again, I am telling the word upper bound. It's not a worst case scenario. It says upper bound function. So whatever the function which are greater than the existing functions, existing time functions. Okay. Now it comes to big of omega. Same definition, only difference will be here we have to find a function of g of n which is less than equal to c into g of n. Earlier in big O omega we are trying to find upper bound, that's why we're looking for function greater than f of n, but here we try to find a function which is less than f of n. So in this case we can say that n g of, if you put g of n equal to n, simply we know that n is less than equal to 2n plus 3, and for this particular NO we have to find at from what value of NO it should start. So in this case, especially whenever you put n greater than or equal to 1, this condition will always satisfy, and here n c value will be 1 into n, so 1 into 1 and 1 into n, 2n plus 3, it will be c, and n naught value will be greater than 1. Okay, so this tells about the lower bound of a function. So when we say lower bound, so for this 2n plus 3, if I write g of n as log n, because log n here in this in the class of space it is less than n. So if I say g of n log n, it's perfectly fine. If I write g of n is equal to 1 also, this also perfectly fine, but because it's a lower bound. But again, as the rule applies, we have to find the function which is nearer, we have to find the g of n which is nearer to f of n. Okay, which is nearer to define the function to get a better approximate value. It's all, whenever we talk about time complexity, is always an approximate. We can't go actually, we can't exactly pinpoint that this is how it is. We always make some assumptions, we always have some approximations. So for, be it for big O or big omega, it will be the same. Okay, so in this case we can directly say that g of n we can take as equal to n, which will be the omega of uh, omega of 2n plus 3. Okay, one question is, Neeraj, can you explain what is currently going on? Okay, we are talking about the time complexity. This is the second part of the time complexity right now which is going on. So this is here in this class we are more focusing on the notation part. Earlier session we talked about how to calculate or identify the time complexity. Okay, now comes the theta aspect of it, theta notation, and this will be of our interest, most of our interest. Okay, so because it gives an average value, if I have to say summarize. Okay, so for this same function we have seen that n, okay, we will at first I will say what is how we can see from the function of 2n plus 3 and 5n. So we have found here this is from big O and for this is for big omega. Okay, so now what is actually happening here is we have a function which is c1 dot g1 which is less than fn, in this case it's n, and then we have something called c2 dot gn, in this case c2 is 5 but gn is n, c1 here is 1 and gn is n, and this a function of fn. So what we are looking at theta function is if g of n in both the big O and say big O and big omega are same, then we can find a theta function. So this will tell us about the average case or aspect of the the particular time function that we are solving for. So if you go with the definition also, for Fn, theta of Gn will be considered as if there is a constant C1, C2 and N naught, such that C1 of Gn is less than Fn and C2 of Gn is greater than Fn. Okay, so if we say that, so for this function we will say that theta would be n, because here the Gn is actually n and we have some constant here, maybe 5 or maybe 1, or we can increase it, decrease it according to our choices. Okay, so we are finding when we have a theta function and when you want to express some function you have written programmatically, we usually use theta. We usually don't use big O or big omega, but certain case we have to use those cases also. We will discuss about why where those cases exist, but for now, for theta you understand that it's a average scenario where for a given time function, can we have a function which can give a average case, that is it comes under upper, it has an intersection, it has an intersection between upper bound and lower bound, upper and lower bound of a time function. So this upper bound lower bound is much needed to understand where the actually a program lies. We will see more about it when we are going to look at the best case and worst case analysis. Okay, so till now we have seen it is big O, big omega and theta in a mathematical way. Okay, we haven't touched the algorithmic aspect here, but given a function called Fn, how we can define big O of big O, big omega, or big theta for a particular function in a more generic way. Now we will try to solve few examples related to that and see that how we can define we can define a certain function, and once we actually go for a algorithmic analysis, how we can put these practices what this practice example into the this example into the actual practice. And again note that this notation are not best case or worst case, it's just one of the ways to tell about a time function. It gives an idea of upper bound and lower bound, from where the upper bound starts or frame or where the lower bound ends. So for example, when we are saying n, so here the n, this n is there on the top, anything which is on the right side is the upper bound. Okay, so anything bigger than n, we are saying that it's a it will become under big O of domain, which is less than n or equal to n, we will come lower bound. Okay, and is this intersection between upper bound lower bound, we will call this as a theta. Okay, if there's no intersection, then there's no theta. If there's an intersection that n also belongs to lower bound and n also belongs to upper bound, then we can say that there exists a theta function. Okay, now let's see few examples to identify how to extract the nearest upper bound lower bound of a given function. So in this case we have fn 2n plus 3n plus 4. So if we have to identify the upper bound, nearest upper bound lower bound, we can do a simple trick here. So if we have 2n square plus 3n plus 4, if you have to make something greater out of it, you, since this is the biggest term n square, you put n square in all other terms as well. That means you put n square plus 3n square plus 4n square, you make it like all n square. Okay, and if you want to make it small in this scenario, so in that case you just have to make n square. You remove all the constants from here, all the other terms, you remove all the other terms, and you just keep n square, which still valid in the equation where n square is less than 2n square plus 3n plus 4. So you have to always keep in mind also that how we can make a lower bound and how we can identify the upper bound. So upper bound, you put whatever the bigger term is there, you just add in any other terms also. So you can find that n square is 2n square plus 3n plus 4, which is less than 9n square. So what it means is, for this particular function fn, what anything which is above than n square, above or equal to n square, we will call upper bound, and anything which is less than n equal to n square, we will call lower bound. So if we have this, and we can see that both the cases here, the n square is still present as a same function. So we can say that we exist also theta. So how we can write it? If you have to write for big of gn, we will write n square. Big omega of gn, we can write n square. See here, constant actually implies, constant is actually giving us some idea of how the how the values are greater than the particular function. Asymptotically it doesn't matter, because the asymptotically, if you actually analyze, constant doesn't matter, but in this case when you're analyzing them, these constants are pretty much matter. And then if you have a theta of g of n, then you can give it as a n square eventually. Okay, so average aspect of this particular function will be n square. This is one way. Okay, now second question also, if we have to try n square log n plus n. Okay, so here whatever we'll try, it's lower bound and this is upper bound. So in this case we will find out if you put n square log n plus n square, this will be bigger than this, and if you just have n square log n here, it will be the lower bound. So anything which is equal and greater than this will come in upper, and which is smaller and till this time, till n square log n, it will be the lower bound. Okay, so here we're trying to find the maximum, that is maximum till in lower bound is n square log n, and here we are finding the starting point. From the starting point till it will be go to the maximum function whatever we have in the mathematics. Okay, so in this case, this is how we can find omega as n square log n of omega of g of n. Big O of g of n we will identify as n square log n less n square, and theta of g of n f n square log n, because this particular term is present in each of these functions and there is an intersection for that. And again, one more thing that I have to tell you here is, we will try that, but n square log n is actually greater than n square. Okay, so we will mostly look at the terminology or the term in a function which is actually the biggest in a particular equation. Okay, that's why we are assuming n square log n for theta. Now we come first a different kind of case. Here is n factorial. So if you have to define n factorial for a function, so we will say that it's a first multiple of first n numbers, n minus 1 into n. So this is how n factorial is usually defined. But if I have to find the upper bound, lower bound of it, and the way we are looking at it, so if we put it here 1 into 2 dot 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 into n. Okay, if I have to find an upper bound of it, I will multiply everything by n, so it will become n into n into n. And if I have to find a lower bound of it, I will just change everything to 1. for better convenience. So I will say 1 into 1 into 1 into 1 into 1, and if you further solve it, it will be become 1 less than n factorial n raised to n. Now, till earlier examples we have seen that there is some similarity in upper bound and lower bound, but here where is NNN and where is this upper bound and this lower bound are nowhere similar. So in this case we can say that the big of Gn will be 1, sorry, big of omega will be big omega of Gn will be 1, big O of Gn will be n raised to n, but there will be no theta. So, and do you have any question with respect to this? Because this is a little important thing to understand here, that there will be a functions where you will find that the lower bound and upper bound and the given functions are nowhere similar. Okay, so we can find here where is n factorial and where is big of upper bound and where it is lower bound. We don't find a common ground here. So if n of 1 is in a time function, is 1 is at particular scale, and if you go till n and then is 2 raised to n and then n raised to n. So n raised to n is a different scale. Okay, there's no in between, which we can call it as a upper bound lower bound, where we can find intersection. Since we don't find the intersection, there's no theta case here. That means we can't find the average case. So if such kind of algorithm you found that where you have a time complexity of n factorial, it's quite very hard to understand all possible cases. It's very hard actually to analyze what will the average case, because they are at two different extremes. Okay, now another example in the same line, with in this case it's log of n factorial. So if we try to solve it again, so I will just expand n factorial here one more time. Okay, now if I have to go again by the same logic, I will just convert n factorial from like I did earlier, that is 1 into 1 into 1, instead of I'm replacing 2 3 from 1 into 1 for simpler analysis. Similarly, I am replacing 1 2 3 from n to get a upper bound, and if you try to solve it, it will become log 1, which is log n factorial and log n raised to n. Now log 1 usually is 0, but for our convenience we can take 1, 0, 1 is same like this. It's a constant function. Okay, it's a constant function, and this is our lower bound, and then we have log n factorial, and then if we try to solve this, it will become n log n. So it will be upper bound. Okay, so big omega will be a constant function, big O will be, sorry, right, one more time. So for f of n, big O of omega will be constant function, big omega, and for big O will be n log n. And an interesting thing to, if you want to analyze here, is just by putting n, the function n log n, the upper bound, has reduced drastically. If you didn't put log here, your earlier for factorial it was n raised to 1, which is in terms of it's quite a big function. But here because of log, it has reduced down to n log n. So log has actually a very huge impact when it comes down to algorithm. So if you're able to write any algorithm which can run in log n time, it's considered very fast. Okay, so from base of the understanding of our definitions of big omega, big O, and theta functions, now the next another thing that we have to understand is how to compare a function. How we can say that it's bigger than which function is bigger than whom. Here when I write directly n log n and greater than 1, I know that okay, since I tried or I know that this is how the function is bigger than other function. But if I have to actually prove them, how we can find it out? So let's take a very simple example. If we take fn equal to n square, gn equal to n cube, one way we can do it, we'll put n square n cube. We just put the values. So if I put 1, it will be 1 and 1. If I put 2, it will be 4 and 8. If I put 3, it will be 9, 27. So you can see that the values, as the input is value is increasing and value is increasing, the distance between these two functions has been increasing. Okay, so that is one way of looking. You substitute some value. Okay, but we will see in next some other examples that always it's not possible, or not it's not possible to calculate. It's very simple functions that we have seen, so it's quite possible. Another way that we can use is apply log on both sides. So how we can apply log is, we just put log n square and then you put log n cube. Here you should have a little bit understanding of logarithms, and you should have a little bit understanding of the formula that we use. So you apply here, it will become 2 log n and it will become 3 log n. So obviously 3 log n is greater than 2 log n, so that's how we can say n cube is greater than n square. So that is one. These two ways we can use to identify which function is bigger. Now, okay, so second is basically apply on both sides. But here some log formulas that I just say in a briefly manner, because we are going to use that we're going to use that in the functions. So if we have log a b, log a plus log b. So if you have a log which a and b, a multiply b, we can is expand it and we can say that log a plus log b. Similarly for log a divided by b, we can say it expanded log a minus log b. And if we have log a raised to b, we can make b log a. So we have seen right now, just like if we have n square, if we put log here a is n and b is 2. So it will, if we expand it, it will become 2 log n. Okay, this is another interesting thing, is if we have a raised to log b base c, you can convert that. You will change this, you place this b with a, and then you can, which is equal to b log a base c. So this is interesting thing that we can look at later. Okay, and if we have a raised to b to n, then if you want to identify the value of b, we can get it directly as b equal to log n base a. Okay, this is something you have to remember. It's not, if it's not remembered, that's still fine. But let's see how we can identify the which function is bigger than what. So first question is if we have n square log n and n log n raised to 10. So given this function, just by looking, we don't understand that which is bigger. And if you try to substitute values also, you should have very good knowledge of log n values and all that. So if we don't have it, then we can just directly apply log on both sides. So if I put log n square log n and here log n log n raised to 10, and then we try to solve it. So if we, sorry, yeah, so if we go by the first formula, log ab, we can divide it as log n square plus log n. Here also same, log n plus log n raised to 10. Okay, and then if you try to solve it again, if this is one and this is another, if you want, you can apply another log in this. So if you apply log on top of it again, if you do not able to understand, so if you do that, it will become 2 log n, it will become log n, 3 times log n, and here it will become log n, it will become 10 log n. Okay, so it become little bit quite complex, but eventually if you do identify that, you will find again we have to see, sorry, it will become 10 log log n. Okay, so if we see if such big equation come to picture, always look at the bigger term, that is log n. In this case the bigger term is log n. So here you check the coefficient value. So here it is 2, it is 1. So based on that you can say that n square log n is greater than n log n raised to 10. Okay, that is one. Another portion that we can look at here is 3n raised to n, and then these two root n log n. Okay, how we can split log a plus b? I think, okay, I forgot the formula here, but there is a formula for log a plus b as well. But okay, if we get it, you will not find such kind of thing, because we will usually see the terminal here function as only one single term. Okay, sorry. I have I made a wrong notation here. I should do log plus log. Okay, if I write more cleanly, I should write it as, if a plus b is there, and if I am applying log, it actually means log a plus log b. Okay, we can't have it. Sorry, that's my mistake. I should have tell earlier. If you have a plus b, and if you try to apply log here, then you will have log a plus log b. You will not have combiningly. Okay, uh, okay. So next question, with respect to this, again, if you try to apply log here, that is log 3n root n, and log 2 raised to n root n log n. If you try to solve it here, uh, you can try to solve it directly. Here we put log 3 plus log n root n, and here we'll get n root n log n plus log 2, and this is our area, this is our area of interest. So we can, for argument's sake, we can remove it but still write it down, and you put apply log here again, log root n, and here it's log 2 is basically 1, so it will become root log n. That is one way. And then if you try to open it, it will become root n log n and log 3, which is a quite minor. So in this case, if you find it, when it comes to if there is a coefficient and main term, if we have it, and there's on the other side there's only one term, we can assume that this coefficient we can remove it. If there's a plus, if it is a multiplication, we can say, so like if coefficient into term is there, then we have to take care of the coefficient. But if it is plus, it is added, that in this case log 3. If that is the case, we can ignore it. So in this case, these functions are actually equal. Okay, so here also we get root log n, here also we get root log n. Okay, that is one way, or there's another direct way that we can use it. I'll try to write it here. So this one function where we can actually transfer log root n log 2. Okay, so based on this third one, where we are replacing b with a, if we use this formula, then also we can identify this, uh, we can change this root log n in the place of 2, and we can put log 2 above. So if log 2 is there, it is initially we consider log with the base 2, so we can consider it as 1, so it will eventually come down to n log n. Now the only thing we have to apply log for only for this 3 root n, which is we already found that it is root log n. Okay, so in this scenario 3 root n is almost equivalent to 2 raised to root n log n. Again, this all are approximation, we are not exactly we are saying that it will be there, but for majority of cases it will be same, almost same. Okay, uh, so let's try two more. I think we have 3-4 questions. Let's try to quickly solve it again. So if you try to put log here, so we will have log n for this function, and for this it will become root n log n, is log 2. So if log n is there, it will eventually become log square n, and this is root n. So usually in a log function, in a function, 1 is less than log n, and any function with respect to log will be less than root n, which is n less than n. So this is how the class has been defined. So if you try to put values also, you can again find it out that log n square will be less than root n. But if you still want, you can again apply the log here and try to find out the what's the value. Okay, you will find out that root n will be still bigger than this log square n. Okay, if we have this 2 log n raised to n, again you can apply log in both the cases. You apply here, you will find log n log 2, and here we will add root n log n. So log 2 is usually 1, so you will say log n, and here root n log n will be the answer, which is usually greater than, because here root n is bigger than log n, so that's why we are saying that n root n is greater than 2 raised to log n. Okay, now third function. Now till we are saying that uh, we usually said that we have, if we have coefficient into term, we have to consider them in a proper value. But if it is coefficient plus term, we can ignore the coefficient, we can only focus on term. So now when it comes for 2 and 3 gn, if you try to apply log also, the value will be still same. So if you apply log here, so it will become log 2 plus log n, here will become log 3 plus log n. If you remove them, is because this is not of our interest, log n actually is of interest, so it is equal. So asymptotically they are equal, value wise they may not, but our focus will be asymptotically, so they are actually equal. Okay, so this function for e function given a 2n and 3n, this is a different kind of case where if you try to apply log also, you find that they are quite the main term is actually same. So in this case also asymptotically 2n and 3n are same. Okay, okay, this I am skimming right now because of time, but we will go to this question. So right now we have seen a particular function with no constraint, but here we have a function where we are defining that for g of 1, n cube will be followed if the value of n is less than 100, n square will be followed when the value of n is greater than or equal to 100. Here in G2 function, n square will be followed when n value is less than 10,000, and n cube will be followed when n is greater than equal to 10,000. So in this case, we should think about which one is greater. So in here we should mostly focus on these values where the constraint actually happen. That is, n is less than 100, greater than 100, n is less than 1000, greater than 1000. So if you put in a line So if you try to put in a line, we will see the try to plot the constraints. So here constraints are basically 100. Uh, anyone can hear me? I think, excuse, okay. Can anyone write in the chat? Can anyone hear me? Because I think my second device lost the connection. So I just want to reassure. Can anyone hear me? Okay, no internet. Okay. Yeah, so okay, turn on the mic. Yeah, so anyone can hear me now? Sorry, I got disconnected because of internet issue. I will just again start the screen. Yeah, okay. So yeah, so we are solving this function where we have gn and g1 and g2 with multiple constraint. So if we want to identify which one is greater, which one is smaller, we try to look mostly at this constraint. So in this case, we can look at the values 100 and 10,000 is there. So what we have to say is below 100 which function will be greater. So here we have seen that if g of 1 where n is less than 100, and here also, okay, n is less than 10,000 is n square. So here g of 1 will be greater because when n value is less than 100, n cube is value uh, is going on. Between 100 to 10,000, we can see that in both G1 and Gn, G2n and G1n and G2n. Here also this n square has been applied. That is n, which n is greater than 100 or n is less than 10,000. Between this, both n square, same function is given n square, so this will be there. But after about 10,000, it will be always G2 because here it has n cube, and we know that we have proved that n cube is greater than n square. So overall we have to look at from, because 10,000 to till infinity, and we want to send which function is much bigger. So we can with proof we can say that g2 is bi- bigger than g1n. Because why? Because after 10,000 value, whatever you write, n cube will give higher value than the n square of the g1 function. Okay, so this is about the function which have multiple constraint. Okay, so if you have to see, for this is a true false condition where they are giving. So what it's saying, so we will have certain function and we have to see whether this equations are actually correct or not. So first let's take n plus k raised to m, and it's saying it should be theta of n raised to m, right? So if we take any value, for example n plus 2 square, so here n is something, k is 2 and m is 2. We know that the highest terminology will be always n square, so n square in this case. Similarly for n plus k raised to m, the highest value or highest terminology, when you expand it, it will be always n raised to m. So when you try to find lower bound, upper bound also for this case, you will have this intersection of n raised to m. So that's why theta of n raised to m is correct. So for this case, we can say it is true. So given a function n plus k raised to m, its theta value we can find it out as n raised to m. Okay, now second question is 2 raised to n plus 1. It's given as big of omega of 2 raised to n. That means upper bound of 2 raised to n plus 1 for a function, it should be 2 of n. So if you try to expand 2 raised to n into 2 here, it will be expanded like this. Since this coefficient is not much of value of our interest, we can still say that 2n is actually upper bound of 2 raised to n. So this is also, we can say it as true. Now the third question is interesting. So we will say 2 raised to 2 2 in raised to 2n equal to big O of 2n. But if you try to expand it, it will be like 4 raised to n equal to, which is always greater than 2 raised to n. So we can't, and since 2 raised to n value is smaller than 4 raised to n, we can't say that big O of 2n is actually correct for 2 raised to 2n. So this, in this case, it will be false. So we have to see the upper bound, lower bound. We are talking in terms of upper bound, lower bound. Since 4 is to 1 itself is bigger than 2 is to n, there's no point of assigning a value less than 4 is to n to have its upper bound. We can't have it. Okay. Now we have, similarly for other function, you can try it out. I will share this when I upload this function. But if you still want, we can try it out here. Okay, so log n, again if you try apply log here, apply log. So if you apply log here, so it will be half log n. Okay, and here its log n is already there, right? So in this case it should be true. Similarly, if you try to apply log here, you will have to see that whether 2 raised to n value is actually less than or say greater than whatever the value you are finding here. If it's there, then we can say that big O of 2n is correct. Okay. Okay, now we'll go to best case, worst case, and average case analysis. So we'll go here from two famous examples, linear search and binary search. So given an array, so we have an array and we have some indexes with respect to it, 4, 5, 6, something like that. Okay. So linear search, how we have to see is, when we say case, we have to see if we are giving a certain input and we are expecting certain output, how fast it should come in terms of time function. So if we say, let's say we have to find the key 4, so we find that it is available at 4. So according to linear search, it will pass through 8, 6, 12, 5, 9, 7, then it will go to 4. So it will be at the position of 1, 2, 3, 4, 5, 6. So it will be at the position of 6, right? So in this case, we are finding 4 at the 6th position. Similarly, for other cases also, we can find at a certain position, but we have to see the best case time in this linear search. So we will say the searching key element which is present in the first index, because the best case that would be it, right? We don't have to spend much time here. We will say that the key that we are searching is actually the first index of that array for the particular linear search. So we will say that for example, if you want to find 8 here, we can say that we had found this in a constant time, because we need only one comparison based on the linear search algorithm. Okay, but what will be the worst case here? So worst case will be the either the last element, or the element is not present. Element is not present. So that will be the worst case. So but since it's the last element, it has to go to the 0 to nth position, wherever the nth position will be. So that's why it will be order of n. I'm saying order of n right now. So what will be the average case? So average case usually defined as all possible case time by number of cases. So in this all possible case time, we will say that what is the time taken for finding 9, what is the time taken for 16, similarly 12, 3, all these cases we have to consider how much time it will take, and we have to see the how many cases it different type of cases it will form. So for that, that's the average case will come. So in this case it will be order of n. Okay. if you actually expand it, it will become n into n minus 1 by 2, and then if you divide by n, you cross n, say n plus 1 by 2. So it will be n plus 1 by 2, the function time will be, but if you approximate it, it will be still a function of n. That's why. This is a best case, best case, worst case, average case time, but you can still write them as omega of 1, big O of 1 or theta of 1. These are all correct for best case. Similarly, you can write omega of n, order of n, and theta of n for the worst case. So these are notation, these are not actually described which is a best case, worst case. Okay, so some asymptotic notation that we see earlier in the session, here we find it that it's just a notation to present that upper bound lower bound actually exists for these cases. Okay, and we can represent it, but worst case best case changes based on the algorithm that we are defining. In this case, linear search is there. But let's see the binary search tree. So I hope you know what is binary search tree. So we will start with we will have some root value. Right side, left side of the value will be less than 10. So I can write 8 and 9 and 6 here, 13, 12, 14. So left subchar will be less than the root, less than parent, and right subchar will be greater than the parent. That's how the binary search has been defined. So for that, best case would be, if you have to find the element from the binary search tree, we will find that, okay, if it is a root, it will be a constant of time. So we can represent it as omega of 1, big O of 1, theta of 1. That is perfectly fine. But this is how the order of 1 we can define if that's a best case time, that the element is that we are searching is at the root. But if it is not at the root, the worst case time would be if it is present at the leaf, that is 6, 9, 12 or 14. These are the worst case time. So we can say that it's a log of n time. Why log of n? Because it depends on the height of the tree, which is log n. So it will take log n comparison to reach till 6, 9, 12 or 14. So that's why worst case time with log n. This is one aspect. But do you think binary tree is only like that? I don't think so. Because there's something called skew binary search tree. In this binary search tree, we'll have like, okay, 10, then 9, then 8, 7, 6. So this is called left skew tree. There's something called a right skew tree. So in this case, best case again will be finding element at the root. So it will be 1, order of 1. But the worst case time is actually n, because you have, if there's a 5 elements in this skew tree, at that time you have to go through all the 5 elements to find the number 6, if that's the key that you're searching for. So here the case would be n, order of n, and you can represent it with any of the case value. So the interesting part here is, for a worst case time we have find something as log n. For a, it's a balanced high tree, and for a skew tree we have found maximum time as n, the function n. So this was a skew tree, skew binary search tree. Okay, so again, if you try to write here n and best case and worst case analysis, you can represent them through any of these three notation. They are perfectly fine, but it should reflect that whether it actually has upper bound, lower bound with respect to that or not. That is something we should take care of over the period of time. We should understand that big O doesn't mean the worst case, and omega doesn't mean the best case. It's just the upper bound, lower bound of a particular function. Okay, and cases, as we have seen in multiple cases, it changes based on different variations, like linear search, or we see in a binary search tree. At the same time, for functions like this n factorial, or for or n square log n plus n. So these are different function, based on different function your values will change, and that is something we should learn and we should practice to understand how we can analyze them. So once you calculate a particular function, then we should try to put in different categories. Which category it should come with? It's come in best case scenario, worst case scenario. If that is there, then what is the upper bound of the function? Can it go more up or can it go more down? So that is something we have to analyze while doing analysis of an algorithm. I think we have crossed the time limit here, but this is the summarization of time complexity that we are saying. For any algorithm, first you try to identify the approximate time in terms of function, and we have seen that we have seen a various big range of function from starting a constant time to n raised to n time. So we have a big range of space of time functions is there, and in that then we try to find the upper bound, lower bound of our time function, and then we try to see in which what are the best case, worst case scenario. So that's how in overall summarize the time complexity of an algorithm, which you should while coding or while explaining to someone, you should have some brief little bit idea of how it actually works. So I think, yeah, that's the end of session. I will stop recording.